In this video, I will demonstrate how to do a confidence interval for a difference in proportions. How detrimental are metal tags to penguins? A study looked at the 10-year survival rate of penguins tagged either with a metal tag or an electronic tag. 20% of the 167 metal tagged penguins survived, compared to 36% of the 189 electronic tagged penguins. We want to give a 90% confidence interval for the difference in the proportions. In this case, we are dealing with a two-proportion problem because we're looking at two categorical variables. We're looking at survival, yes or no, and metal tags versus electronic tags. First thing we want to do is define the parameters. Because we're dealing with two proportions, then we have two proportions to define. So let's define P1 as the proportion of surviving metal tagged penguins and P2 as the proportion of surviving electronic tagged penguins. When we're talking about the population parameters like we are here, then what we're really talking about is the proportion of all penguins who would get a metal tag that would survive and the proportion of all penguins that would get an electronic tag that would survive, not just the ones from our sample. Next, we look at the appropriate sample statistics. Since we're looking at a difference in proportion, the appropriate sample statistic is p hat 1 minus p hat 2. Our problem told us that 20% of the metal tagged penguins survived and 36% of the electronic tagged penguins survived. So that would be 0.20 minus 0.36 is negative 0.16 for our appropriate sample statistic. When it asks for the correct notation is this p hat 1 minus p hat 2, and the correct value for the sample statistic is the negative 0.16. Our formula for doing a confidence interval for two proportions looks like this. We have p hat 1 minus p hat 2 plus and minus z star times the square root of p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. This whole square root portion over here is the standard error portion of our confidence interval. And if you recall, the standard error for the difference of two proportions normally has P1 and P2 in it, which we obviously don't know. So when we're doing a confidence interval, our best estimate for P1 and P2 are going to be p hat 1 and p hat 2. So you can see that they've been substituted here in the formula for the confidence interval. So first we need to know what is our value for z star. And our problem stated that we wanted to have a 90% confidence interval. So we can use the normal distribution in StatKey to help us figure out what z star should be. In StatKey, if we click on two-tail and then we change the value in this center box here to be equivalent to our level of confidence, which in our case was 0.90, then the value down here on the axis in the box is going to be our z star value. So for 90% confident, our z star is 1.645. All right, now we need to make sure we have all the other important information in order to use the formula appropriately. So we already had p hat 1 and p hat 2 were 0.2 and 0.36. We need to know n1 and n2, as you can see down here in the formula. So n1 was the number in our sample for the metal tags, which was 167. N2 is the number in our sample that were electronically tagged, which is 189. And then we just barely found z star to be 1.645. We can also determine the number of successes just by multiplying the proportion of successes times the sample size for each of our samples. We don't expressly need the number of successes in our formula, but the requirement for using the normal approximation is that our number of successes and number of failures are all at least 10 or more. So we kind of have to figure that out to be able to check our conditions. So first thing we do is check our conditions. We want to make sure that all of the successes and failures, or you could think of them as yeses and nos, are at least 10 or more. So we had 33 successes in the first sample. That's bigger than 10. And 134 failures, also bigger than 10. In our second sample, we had 68 and 121. All of those are bigger than 10, so we do meet the requirements for the normal approximation. Here is our confidence interval formula. Now it's just a matter of plugging in all those numbers that we found earlier and solving. So if we take all those numbers and plug them all in, then we work our way down so that we get a confidence interval that goes from negative 0.237 to negative 0.0834. Now, this is a pretty complex formula, and rather than getting bogged down with all the calculations of all this heavy-duty calculations, really, then there is an easier way to find the standard error. So remember, the standard error is this whole section over here underneath the square root. There's our standard error. And there is a handy-dandy website that will compute the standard error for you for problems like this. So this website has these visualize applets that will calculate the standard error for you. So this will be especially helpful in your homework, like in Wiley Plus, where when they ask you to find standard error or to compute a confidence interval, you can feel free to use this visualize applet to find the standard error for you. On exams and on the written homework, then I will give you the estimate for the standard error. So you won't be expected to do this big nasty formula section on the exam. So let's go over to the applet so you can see what that looks like. So once you go to the website, here's what it gives you. And in this case, we're looking at a difference in sample proportions. So I want to click on the SE for sample proportions. Once I click on that, it's just going to ask me to enter the successes and my sample size. So I already calculated my successes to be 33 for the first group, and my sample size was 167. And for sample 2, I had 68 successes out of 189. Once I get those in there, remember that the standard error is different when we're dealing with proportions, depending on whether we're doing a confidence interval or a hypothesis test. So we have to make sure we choose the right one. In this case, we're doing a confidence interval. So I click on confidence interval and click on compute standard error, and just like that, it gives me the value of the standard error to be 0.04656. So I can take that number and just replace the big nasty part in my formula. If I go back here, I'm going to replace that whole big square rooted thing with the number that I got from the applet, that 0.04656. That's my standard error. And then I can just solve and compute the rest of the confidence interval like normal. So once I do that and I multiply times z star, I end up with a margin of error of 0.0766. And then, of course, I get my confidence interval that goes from negative 0.237 to negative 0.0834. So I interpret this confidence interval just the same way that we've been interpreting confidence intervals since the beginning of the semester. So we would say we are 90% confident that the survival rate is between 0.0834 and 0.237 lower for metal tagged penguins as opposed to electronically tagged penguins.